today's video, we will summarize the overall content we've covered so far about Habitat 67. Habitat 67 is a pioneering example of modular architecture located in Montreal, Canada. Designed by architect Moshe Safdie for Expo 67, this innovative housing complex consists of 354 prefabricated concrete modules, all of the same size, arranged in various configurations to create 146 residential units. Each unit is designed to offer the benefits of both suburban homes and urban apartments, including private gardens, terraces, and ample natural light, while maintaining the density and efficiency of high-rise living. The modular construction method used for Habitat 67 involved manufacturing the modules off-site factory nearby the site and assembling them on location, which allowed for rapid and cost-effective construction. This approach not only showcased the potential of modular housing to address urban density and housing shortages, but also demonstrated the flexibility and adaptability of modular design. Habitat 67 remains an iconic architectural landmark and a testament to the innovative possibilities of modular construction. Habitat 67's modules were prefabricated in the factory around the site to ensure precise construction and efficient assembly. The process began with the molding of the basic modular shape in a reinforced steel cage. Once the 90-ton concrete boxes were cured, they were transferred to an assembly line for the insertion of electrical and mechanical systems, insulation, and windows. In particular, in the later part of this video, we will take a closer look at the MEP system. Modular kitchens and bathrooms were then installed to finalize the production. Finally, a crane moved and lifted each unit to its designated position, allowing for the unique and complex structure of Habitat 67 to take shape. Habitat 67 was planned to be constructed on the artificial landmass created for Expo 67, which means the ground is weaker than other areas. Therefore, it was necessary to effectively drive piles to distribute the load of Habitat 67. A total of 1,120 piles were used in Habitat 67, with 3 to 4 piles in each pile cap. The length of each pile was approximately 6 meters. These pile caps were concentrated in areas where large vertical loads were applied. In the drawings, you can check that the piles are concentrated under the vertical elevator towers, columns, and the bottom module clusters, which bear the largest vertical loads among these structures. Once the foundation work was completed, cranes moved and lifted the factory-produced modules to their designated positions. Various types of cranes such as gantry, derrick crane, were used to transport and lift the modules into place. The movement path of the crane was primarily located along the St. Lawrence River, providing an efficient route for transporting precast modules from the plant yard to the construction site. Along the path, the gantry crane moved modules to their designated positions on the construction site. This allowed the derrick crane to lift the modules to higher locations as needed. The lifting process was facilitated by an adjustable cylinder, which created a flexible frame for precise lifting and moving. Typically, the lifting process would involve directly attaching straps or slings to the object, allowing for flexibility through the adjustable trolley. However, in the case of Habitat 67, since all modules were identical in size, there was no need for an adjustable trolley with flexible positioning rails. This approach is similar to using a modular spreader frame, providing an efficient and consistent lifting mechanism. The crane, lifting frame, module connection was achieved by attaching steel chains or straps to the lower part of the frame. These chains were equipped with hooks that were used to connect the frame to the module. This method ensured a secure lift and precise placement of modules into their designated positions. The use of hooks provided flexibility and ease of attachment, contributing to the overall efficiency and safety of the construction process. The combination of crane types, movement paths, and lifting methods enabled the construction team to efficiently and accurately assemble the modules. This ensured the stability and quality of Habitat 67 throughout the construction process and demonstrated the successful application of innovative construction techniques. So far, we've observed that Habitat 67's modules are not simply lifted and stacked in a straight line, but pop out here and there. This raises a question. How can the modules be stacked without collapsing during the stacking process? If we place a module at the bottom and then stack another module on top in this manner, the structure would likely be very unstable and collapse, unless a substructure capable of supporting the load of the modules is installed before placing the modules on top, or unless modules are not stacked directly on top of each other immediately after placement. The structure would collapse under the weight of the module placed on top. However, in the actual construction process of Habitat 67, neither substructures were installed nor were modules stacked directly on top of each other. The reason for this can be understood when viewed from above. In each floor, two modules were arranged in an L-shaped configuration, and on top of them, another two modules were arranged in a similar way. This L-shaped pattern arranges in space next level generated by rotating the lower module by 180 degrees. The same operation is used to generate the next level. Roof of the lower level becomes terrace space. Next level were generated by mirroring the lower module and then rotating by 90 degrees. Different terraces are created due to the different operations. Like this, stacking two modules per one floor in an L shape, totaling 4 floors, forms a cluster. Each cluster consisted of 8 modules, and clusters were tied together with post-tensioning cables, creating a single structural entity. This allowed modules to be stacked one by one without the need for substructures or counterbalancing modules to prevent collapse from above. As evidence, numerous photos from the actual construction of Habitat 67 demonstrate modules positioned stably without the need for substructures or modules providing counterbalancing forces from above. However, if the modules are not aligned vertically and horizontally during the stacking process, resulting in gaps between the modules, it would be very dangerous. Ensuring vertical and horizontal alignment is crucial not only for safety, but also for the overall structural stability. Now, let's explore how vertical and horizontal alignment was achieved during the module stacking process and how this alignment was verified. First, to align the modules horizontally and vertically during the lifting process by the crane, adjustable cylinders and adjustable trolleys sized to fit the modules were installed. Although all modules were of the same size, the walls of each module had different openings depending on their designated location, which means each module has a different center of gravity. Therefore, the adjustable cylinders were adjusted to distribute the weight of each module accordingly. Secondly, the modules lifted by the crane were positioned using pre-calculated points groove to maintain their alignment. These grooves served as the connection joints between the modules, ensuring vertical and horizontal stacking. Also, grooves allowed the modules to interlock, forming a more solid structure and maintaining stability. The gaps between these grooves were filled with high-strength grout. Finally, once the modules were fitted into the grooves, the modules were secured by connecting the post-tension cables while maintaining their vertical and horizontal alignment. Just as the modules wouldn't fit properly into the grooves if they weren't aligned correctly, the post-tension cable connections wouldn't align if the vertical and horizontal alignment was off. Therefore, the vertical and horizontal alignment was verified both by fitting the modules into the grooves and by connecting the post-tension cables. Even after going through various verification procedures to ensure that the modules were perfectly vertical and horizontal, the stacked modules were finally checked using a level, as you can see in the photo. However, no matter how well the foundation work is done and how precisely the modules are stacked vertically and horizontally, if they are not tied and secured together but simply stacked, Habitat 67 would be a rather unstable structure. To enhance the structural stability, Habitat 67 is interconnected through post-tension cables. Let's take a closer look at the post-tension connections within Habitat 67. First, we will briefly introduce a post-tensioning method regarding the connection and bonding of Habitat 67. Before pouring concrete, a duct for accommodating pre-stressed steel strands is placed. Then, concrete is poured and cured, and PS strands are inserted into the duct. The inserted strands are tensioned to provide pre-stress to the concrete. Tensioning of the PS strands is done using tensioning equipment such as pumps. Once tensioned, anchorages such as screws or wedges need to be installed. The post-tensioning method requires anchorages to secure the steel to the concrete, but since the PS strands are tensioned after the concrete has set, it is suitable for on-site construction. This method allows flexibility in choosing the number and layout of PS strands and enables the construction of various shapes of members. The diagram shows how the post-tension cables run through the concrete of each unit. It also shows where the steel rows would be placed in order to stack the units. First, we will divide the diagram into sections A to D and explain how the post-tension cables are connected within the concrete of a single module in each section. Let's begin by looking at section A. Upon closer examination of section A, we can see that it closely resembles the current modeling. Using the bar grid, bars are securely fixed within the member at predetermined locations. The bars fixed in section A are connected all the way to section B. Let's take a closer look at section B. Section B is where the post-tensioning method is employed. Similar to section A, bar grids are used to secure bars at predetermined locations, and section B is positioned on the walls of the two modules to be connected. With the T-shaped section of section B, holes are also drilled for two reinforcing bars. After fixing the bars in section A, the opposite side in section B is pulled by a post-tensioning machine, and then the protruding parts of the bars are cut, filled with grout, and finally finished with sealant. So far, we've examined where the post-tension cables were installed inside the modules and how they were installed, as well as how the final finishing was done after installation. Now, let's explore how these modules are connected and bonded to each other when stacked vertically, horizontally, or side by side. The joints where modules are connected are indicated by section C and D in the current modeling. Let's first examine section D. Firstly, as seen in the modeling, the current area indicated by the arrow represents the outer face of the lower module. The portion currently marked in red denotes a pipe sleeve with a diameter of approximately 90 mm, within which fits a pin measuring about 65 mm in diameter and approximately 400 mm in length. The section highlighted in red represents a steel plate positioned at the joint between modules with sponge rubber and neoprene pads placed adjacent to it and above it, respectively. All the structures described are secured by several reinforcing bars with a diameter of approximately 13 mm. Finally, high-strength grout is injected between the pipe sleeve and the pin via an approximately 13 mm diameter grouting tube located at the top, firmly and robustly bonding the two modules together. When stacking modules on top of each other, steel plates, sponge rubber, neoprene pads, and similar materials are used between the modules. The reasons for using these materials are as follows. First, they reduce vibrations between modules, increasing stability. Second, they decrease friction between modules caused by various impacts or external factors, thereby enhancing the building's durability. Additionally, these materials compensate for any imbalance that may occur during the stacking process, ensuring safe stacking. So far, we've covered the explanation of section D. Now, finally, let's delve into section C. We will also explore how the connections between modules were achieved overall. In section D, we focused only on the areas where modules are in direct contact with each other. Now, in section C, we will explore not only the points of contact between the modules, but also how the connection between modules is achieved overall. First, in the plan view of section C, you can see that there are two reinforcing bars embedded in the rectangular frame at the center of the wall, with grouting tubes on either side of the rectangular frame. The modeling you are currently viewing is a vertical section of section C. First, the lower section is the lower module, and the upper section is the upper module. The part indicated by the arrow is the grouting tube you saw in the plan view of section C earlier. The part represented by the red line is approximately a 25 mm diameter tendon, and the two tendons are fixed to the upper steel plate. Similarly, the void space between the concrete and the tendon is filled and firmly secured using high-strength grout injected through the grouting tube. Now, let's take a closer look at the parts where the modules are directly connected. The part indicated by the arrow is the coupler shield. The coupler shield is one of the accessories used for rebar connections. Typically, used when connecting two rebars to create a longer one, the coupler shield is used to protect the connected rebars and ensure a safe connection. Above the coupler shield is the end shield, which is also an accessory used for rebar connections. Typically, it is used to protect the end of the rebar and ensure a safe connection. The end shield covers the exposed end of the rebar, increasing its safety and preventing damage during the rebar connection process. In the section where the modules directly meet, you can see that steel plates, sponge rubber, and neoprene pads introduced in section D are used. The currently displayed part is asphalt coated. The asphalt coating around the junctions of modules in Habitat 67 serves two main purposes: waterproofing and surface protection. It helps prevent water infiltration and dust accumulation, enhancing durability and protecting the structure from environmental elements. Additionally, it safeguards the integrity of the junctions, extending the lifespan of the building. Finally, at the bottom, you can see the anchor plate, sized 100mm by 100mm by 6mm, which securely ties together the structures mentioned above. So far, we have examined the post-tension cable connections within individual modules and between modules. However, almost every structural component of Habitat 67 is composed of modular units, and these are also connected using post-tensioning techniques. The elevator core, pedestrian walkways, staircases, and many other structural elements are all tied together with post-tension cables. Among these, let's delve deeper into the elevator core and pedestrian walkways, which form the backbone of Habitat 67. The three elevator cores in Habitat 67 are among the most crucial structural elements of the complex. Each elevator core is composed of modules, with each module spanning 4 stories. By stacking 3 of these modules vertically, the 12-story height of Habitat 67 is achieved. The elevator cores are connected to the pedestrian walkways cores at each connection point using post-tension cables. An important detail, evident from the modeling and design blueprints, is that while the elevator cores are directly connected to the pedestrian walkway cores, they do not directly connect to the residential modules. This means there is no direct interface between the elevator cores and the modules. Finally, let's examine the post-tension cable connections of the pedestrian street cores. The pedestrian street cores needed to extend from the elevator cores to the farthest residential units, requiring the connections of 3 modules. Identical sized modules were attached to each other, ensuring that the post-tension cable connection points overlapped. These connected modules were then extended by adding more modules, 2 to 3 at a time. The extended length necessitated strong connections between the modules, achieved using post-tension techniques. The post-tension cables within the connected modules were installed as shown in the current visuals. The visible groups were designed to connect the modules, with the connections also made using post-tension cables. Unlike the elevator cores, the pedestrian walkways were connected to some modules with post-tension cables, allowing them to share and distribute structural loads effectively. Next, we will examine the construction and finishing of Habitat 67's walls, exterior surface, and terraces, followed by an in-depth look at the MEP systems. We will look into Section A, where each module contacts the exterior, Section B, where modules connect with each other, and Section C, which concerns the terrace area. First, let's take a look at Section A. Section A is where the modules are directly exposed to the external environment. In the original Habitat 67, the walls had minimal insulation, leading to durability issues and leaks over the years, making it vulnerable to the harsh Canadian winters. These weaknesses are addressed in a major renovation in 2017. Before the renovation, the concrete walls were insulated with only wooden battens and about 10 cm of basic polystyrene insulation. After the renovation, the existing wood and polystyrene insulation were removed and replaced with a Z-girth system. A Z-girth system was installed against the wall and insulation was added. Smart vapor retarder was installed to allow the wall to dry either toward the inside or the outside depending on the direction of the water vapor flow, which is directed by temperature and or water vapor pressures. The Z-girth system is a specialized exterior cladding system applied to the outer walls of buildings. It typically involves covering the exterior walls with a mixture of cement and gravel known as a girth, enhancing the building's protection from external elements and increasing its durability. The Z-girth system helps improve the robustness and longevity of the building envelope, safeguarding it against wear and tear over time, and providing protection from weathering and climatic changes. Now, let's examine Section B. Section B represents the area where modules meet each other, and the most crucial finishing detail in this area is the perimeter. In this perimeter area, besides the sealant and aspartame coating mentioned in the previous video, protective mortar was applied to maintain integrity. Lastly, let's examine Section C, the terrace area. Each unit in Habitat 67 has at least one terrace, which is an important space. The primary concern here is how to properly drain water from the terrace. Without an adequate drainage system or proper finishing, maintaining the terrace would be difficult, especially during rain or when watering plants. First, let's look at the drainage system. The terrace is slightly sloped to direct water to a drain located at the center of the terrace. To ensure water flow to designated drain locations, roof modules with a 1:100 slope were also prefabricated in the factory. During the prefabrication process, levels were used to measure the slope to direct water from the terrace edges towards the center. A consistent layer of sand was laid down, and then rubber mollets or flattener were used to compact the surface to achieve the desired slope before finishing with concrete. After the concrete was set, waterproof treated timber was installed as the final layer. This timber protected the concrete surface from damage and was easy to replace if needed. While this method might seem primitive, it was the best available option considering the era when Habitat 67 was built. An article from the May 1967 issue of the America Architectural Forum stated, all thermal along a large crew of workers tend to over 200 individuals' roofs. This confirms that over 200 module roofs or terraces were constructed by workers on site at that time. Finally, let's take a look at the MEP systems of Habitat 67. Before discussing the MEP system, let's first explain the subfloor of the module. During the manufacturing process of Habitat 67's modules, the bottom part of each module features a structural framework, upon which the actual flooring, stepped on by residents, is installed. Beneath this framework, various cables, pipes, fan coil units, and ventilation shafts were installed. These components, including electrical outlets and ventilation controls, are positioned close to the floor, as seen in the photos, due to the presence of various MEP elements installed at the bottom of the modules. This subfloor is one of Habitat 67's great technical inventions, a 600 mm deep space under the floor that provided for air conditioning equipment and ducts, plumbing, and electrical routing. It proved to be the element that really gave long-term flexibility to the building. The subfloor also allowed residents to move bathrooms and kitchens to wherever they wished, to rearrange ducts, and to repartition the space. With the concept of this subfloor in mind, let's delve into the MEP system in detail. First, let's look at the plumbing system. Habitat 67 features a centralized drainage system. Each module of Habitat 67 is connected to a central drainage pipe, enabling effective wastewater management. The drainage pipes extend throughout the entire structure, with individual drainage pipes from each module converging into the central drainage system. As shown in the current images, these central plumbing pipes are marked and serve as a guideline when stacking the L-shaped clusters. Similarly, a central plumbing pipe was installed beneath the pedestrian walkway core, which was mentioned earlier. Next, let's explore the electrical supply and wiring system. Habitat 67 features a centralized electrical supply system. Similar to the drainage system, the power supply in Habitat 67 originates from the central electrical room located on the first floor, which distributes power to all individual modules. Electrical power is supplied from the central electrical room to each module through connected distribution panels, and each module also has its own distribution panel to manage the supplied power. Wiring for power supply, like the plumbing system mentioned earlier, runs along pipes spanning the entirety of Habitat 67, branching out to each module. The location of the electrical room can be identified on the drawings, and for a more detailed understanding, you can check the exact location of the electrical room in the modeling. The previously described subfloor of Habitat 67, plumbing and electrical system of Habitat 67 allowed for the flexible placement of bathrooms and kitchens with the modules. The reason bathrooms and kitchens could be installed freely within the modules was that modular bathrooms and kitchens were used. Given that these were not installed together with the module, you might wonder how water supply and waste management were handled. During the manufacturing process, once the positions for the modular bathrooms and kitchens were determined, the necessary plumbing and electrical wiring were pre-installed in the subfloor. These pre-installed pipes and wires were then connected to the modular bathrooms and kitchens to supply water and electricity. The drainage of water and waste was also routed through the subfloor and ultimately connected to the main MEP system of Habitat 67. In drainage pipes, an anti-siphon trap was installed to avoid the possibility of the trap seal being drawn away by siphonage within the waste system. It prevents unwanted backflows of water and bad smells. Note that none of the toilet blocks have an external vent. This is to prevent any foul smell or methane leakage in the neighbor's roof garden. Instead, all these utility services open up into a duct, which has proper vent stack connections and exhaust. Additionally, you might be curious about the heating systems. Habitat 67 employs a central heating and air conditioning system. As you might have seen on the electrical room drawings, the boiler room is located right next to the electrical room. The heating system is set up to supply hot water or steam from the boiler room on the first floor through central pipes, which we mentioned earlier, to each module. Throughout this semester, we have explored various aspects of Habitat 67 designed by Moshe Safdie. From its conceptual background to its construction details, we particularly focused on the precise lifting of prefabricated modules using cranes and how different structural elements of Habitat 67, such as modules, elevator cores, and pedestrian walkways, are connected using post-tensioning techniques. Finally, we delved into the MEP systems in detail. We hope that the videos we produced this semester have provided you with a comprehensive understanding of the construction process of Habitat 67. Thank you very much for watching our Team 7's final presentation.